recording. Okay, so I'll cover the assignment 3 topics today. Maybe the last one, the source follower. We'll see how much time we get. I did not get a chance to look at a lot of your assignment because I actually need it on Monday because, you know, after I come back from work, I usually don't get enough time. But I'll take a look at it, make sure, you know, if you guys have any problems, I'll solve that. But I'll cover the topic in a pretty wide manner, so you should be able to get an idea. I think pretty much all of you probably understand the topics. I'll maybe give you a little bit of insight on some of the concepts of it. Okay, before I start, I'll quickly recap what we did last time. So I think we left at the low frequency small signal model. So I'll just quickly tell you how to create a small signal model. I think all of you are getting hang of it, and most of you have probably done a lot of the BJT small signal models. So if you have a circuit like this, for example, let me just switch. So if you have a circuit like this, so you have some DC bias, for example, in this case, you give a certain VGS to bias this transistor here. So this is like a source follower gain stage, which I think is part of the assignment, which you have done some problems related to it. And then you bias it with a certain current IB, let's say. And let's say I want to find out the small signal gain between V0 over Vi. Because this is a nonlinear device, we said that we need to linearize it, and that's why we do small signal models. So just like the quick 3 main steps is if you have a small signal model like this, so you want to first set all small signals to 0. Like, for example, this Vi to 0, because this is a voltage source, this will become a short, right? Once you set that, then find all the DC operating points. So when I mean DC operating point, the small signal parameter, like the transconductance of this, the GDS of this, the backbody effect of this, and so on. So that's your linearized DC operating point. And if this small signal was a current source, that will become an open. Obviously, you cannot have a small signal current source going into a high impedance node. In this case, you short this. So you get a VGS. For that VGS, you find out what the GM, and for IB, what the RDS and GS is. Then in order to draw the small signal, you basically set all the large signal elements to 0. So again, the voltage source becomes short, so the supply will actually become a short to ground, so this will actually become a ground. The gate source voltage, DC voltage, will also become a short, and so you'll basically connect this small signal to ground directly, and this current source will become an open. Now, typically this current source will have some output impedance from here across this node. So you usually have R0. For this particular purpose, we have it open. So if you do that, you'll get a small signal equivalent model. So this part here is nothing but the transistor small signal model, where you have a small signal from the gate to the source node, and the source is ground, so that's why this is ground. And then between the drain and source, you essentially have 2 elements, the transconductance times the gate voltage, which is the input voltage, and then the output impedance, which is RDS. You also have the backbody effect, which is the GS, but in this case, I'm simplifying it by saying that this source is connected to the grounds. So because your bulk and the source are connected together, then that term goes to 0. So I haven't drawn that. Then I have drawn this, actually, sorry, maybe I shouldn't have said that there is no R0. So this IB, when you make it to 0, it still has a small signal element to it, which is R0 from V out to ground, because this is shorted here. So you essentially get the output impedance of this transistor in output impedance parallel with output impedance of the current source. And that's your actually total output impedance. And I think when you do the common source example, it'll be much more clearer. So that's sort of a quick recap on creating small signal models from a large signal equivalent. So why current mirrors? So the first topic, why do we need current mirrors? So mainly for two purposes. One is to provide bias current for multiple blocks. So usually what we have is we have a single pristine source, which is usually from a band gap or some reference source. And we have multiple circuits inside the IC and we want to copy them. That's the easiest way to bias them. And probably maybe some other time when we do references, I'll explain why do we current instead of voltages. So there's a good reason for that as well. And the second reason we use these current sources are for active loads. And I'll explain soon what does active loads mean for amplifiers. So these are the main two purposes we use current mirrors for. So this is what I mean for biasing different circuits. So usually this is a pristine current source which is given to you, whatever that current source is from a band gap or other reference. And we create these copies using these current mirrors in one place. And again, I won't cover in this lecture, but maybe when we cover references from a project point of view, I'll explain why we don't separate this out. Why don't we keep these mirrors here and just transmit the voltages? So we have, like for example, N circuits here, we take that current and mirror it and provide each of this leg to each of these circuits, and they provide the bias current for each of those circuits. So that's really what I mean by biasing current. Okay, why active load? So taking a simple example here, I think it was one of the problems, first assignment 1.19. This is a common source amplifier actually. So you have an ideal current source with 200 microamp, and the output impedance of this we had calculated to be 20K. So the self gain was about 35, and we biased it to this 0.7 volts, and we wanted to find out what's V naught over Vi, right? Now, if you just take this transistor by itself, its transfer characteristics is this, right? So if this is VDS, so this is VDS as well as V out, because VDS is nothing but V out because it's with respect to ground. So this is VDS as well V out. So if I change the bias voltage in a large signal manner, this is how the curves will look like, right? We covered that when we covered the transistors. And these three different curves are for three different VGS. So when I'm giving a small signal, the VGS is going to change. So these are the transfer curves for each one of them. And I've kind of exaggerated the output impedance by showing that it's a slope, it's not constant. Now the reason we get gain is, so if we want to find out delta V, like this delta VI input versus delta V out, which is really the gain, I want to see what this operating points are if I put this current source. So for example, this current source 200 microamp, let's say this is 200 microamps. As I'm changing V out, if this was the ideal current source, it still should remain the same, right? Because that's the ideal current source. So if you take these two graphs, the output voltage V out is actually these 3 points, because that's where they intersect. You can, those are the solution for these two to satisfy both the current source being ideal 200 microamp and this nonlinear device which follows this, right? So I kind of show graphically. So if you have a certain delta Vi, which is VGS, it's basically switching between these two curves here, right? Three curves here. And my current is always constant. So as I'm switching through these curves, actually my operating point is moving along this line over here. So if I give a small sinusoid input over here, then I get a large sinusoid output over here, right? Because this current is constant, and I need to my solution put to this point, having these two currents over here are only these points over here. I cannot be on this this over here, right? So if I give us delta Vi over here, I get a delta V out. And we have seen that with the small signal model. So essentially, this is sort of taking a large signal solution of the small signal model. So the key point here is that the bias current is independent of the output impedance. In other words, I can change this bias current to any value I want. I'll still get that high gain. Well, the gain might change, but I'll still get a high gain. But that, so the question when I said why active load, what I mean by that is why not just put a resistor, right? So we had calculated a certain impedance of a current mirror in the later examples. Why not just put a value of that resistor? So the problem with the resistor is this. So I take the same example again. I apply the VI 0.7, same W over L, same RDS for this transistor. Now, in order for the same current to flow in, which was, what is it, 200 microamp, so I need, so usually I set this to 0.9 volts DC, right? So that it's at a midpoint. So let's say the supply is at 1.8 volts. I want the output to be at 0.9 volts. Now for that to happen, this RL needs to be at 4.5. It cannot be anything else, right? Because if I need 0.2 milliamps in this resistor and I need this value to be 0.9 and this is also fixed. So I have 1.8 volt fixed, I have 0.9 volt fixed, I have the current through this fixed, then my resistor is fixed. It's a linear device, right? So if my resistor is fixed, then my, so if I do the same sort of thought experiment, if I'm going to solve this current through this branch, it has to satisfy both this resistor as well as this transistor. So the transistor follows this curve, which we said before. Now, if I draw the load line of the resistor, for the current it was just a flat, but since I have a resistor, as I change V out, the current through this RL is going to follow this pattern, right? That's your load resistor. Now that means the solutions are these points now traveling through this. So if I do the same thought experiment again, if I change the delta VI, I'm going to get a certain V out. But for a given current, I'm fixed with this R, right, RL. Now, as you can see, this is about 4.5K and this is 20K. So really, this sets my gain, which is a lot lower than RDS. For example, you do the self-gain calculation again, like GM times RDS like you did before. Now it's GM times RDS parallel with RL, which is almost equal to RL because here I calculate it's 4.5K. So instead of getting, what do we get, 35, gain of 35, now we're getting gain of 28. So that's the key point. If I can't always use resistors. Sometimes for really fast devices, we actually use resistors, but for most circuits, actually we'll use a current source. And the key again is the bias current and the output impedances are not independent. So I can set the bias current and have any impedance I want. And so I can independently set the current and the gain depending on how I want to minimize area or minimize power and so on. And the other thing is that in IC design, this RL is usually expensive in area. It takes a lot of area to build these resistors. So they're not usually cheap in area terms to build resistors. So that's the other reason we avoid it too. Okay, how do we create a current mirror? So the current mirror is nothing but copying a current, right? So you take, like as I showed in the previous example, you take I give you a certain pristine current source and you take that and you copy it, right? So I'm going to just, okay, so if I draw that here, so I give you a certain current source with reference to VDD, could be reference to ground, anything, doesn't matter. So I give you certain current source, and this current, let's say, is some value. Let's say this is your, I call it IREF, and let's say it's 80 microamps or whatever it is, and I ask you to basically copy this, right? So if I need to copy it, the first thing I need to do is I have to first measure it, right? So I'll put something like an ammeter. So this is more of ideal. So like, let's say, you have your current meters in the lab. So if I put a current meter here, so this current meter will show that, oh, this current is equal to 80 microamps, which is flowing in this. Because this is usually a very low impedance current current meter, ammeter, like voltmeters are high impedance, current meters are low impedance, right? So I measure this and I say, okay, I give you a certain technology. I give you a NMOS technology. Let's say this is your NMOS. And let's ground this in reference to ground. And I say, okay, what is this VGS value that will make this ID equals to 80 microamps? And if I take, and I'll just take the example, I think one of the examples we have. So if we take the point, I think 8 micron technology we are using. So if I take a NMOS of that, so the beta and beta, which, from now on it's mu n Cox. So instead of writing mu n Cox all the time, I'll just write beta. That's 90, if you look at your table, I think that's 92 ampere per volt square. And the VT for this device is 0.8 volts. And let's say I give you a W over L of 100 micron by 1.6 micron. Okay, so if I give you this technology and I give you this W over L size, basically I ask you what VGS you need for producing that microamp current. And so let's assume that there is no output impedance. The lambda is essentially 0. Then the current equation is just ID times beta, where beta is this mu n Cox here, beta times W over L VGS minus VT square, right? So which means that VGS minus VT is just square root of ID over beta times W over L. So if you plug all these variables here, which I've given, if you calculate it, I've already calculated, so I'll give you the number directly. So it's 0.118 volts, approximately 118 millivolts, okay? So the VT is given as 0.8 volts. So basically VGS means VGS is VT plus 0.118 volts, which is equal to 0.918 volts, right? So if I take this voltage and apply this, then I'll get a current of 80 microamps, provided this drain to source voltage is what? VDS is greater than what? V effective, right? Which is in our case equal to 0.118 volts, 180 millivolts. So as long as I have 118 millivolts across this, then this transistor will generate 80 microamp of current. So the next question is, how do I generate this voltage? I know what voltage to apply in this transistor to get it. How do I generate it? Actually, let me just bring in a new slide here. So one of the ways to generate is, or probably one of the primary ways to generate is, you actually take the same transistor size. So we said we're going to take a NMOS, and I'm going to just put that I ref over here. This I ref equals to 80 microamps, let's say. I'll put it here, and the W over L, I'll make it the same, which I think said 100 micrometer by 1.6, right? Now, why does this generate the same VGS? Because this current, so we have to satisfy KCL here, right? So this current should be equal to whatever current is flowing out here into the RDS. So let me just redraw this again, sorry. So I'll try to exaggerate this. Okay, so if I apply KCL on this node, so let's say this is base current IB, and that's your drain current ID. So IREF should be equal to what? ID plus IB, right? But in steady state, what is IB? This is not a BJT, right? This is a MOS transistor. So there is no gate current. We usually don't have gate current. So this is usually 0. So which means that ID is equal to IREF. So it has to, in the only way this VGS will go to is when the ID or the steady state value of this VGS, this gate to source value, the VGS, will result in such a value that ID has to be equal to IREF, because otherwise the KCL won't be valid here. Now, if you look at it transiently, so how does it happen automatically? Well, if I draw, let's say, graph of this, right? So let's say this is time, and this is your ID, and let's call it ID and IB and IREF, right? So the IREF is always constant. So IREF is this 80 microamp here. And this IREF has to be equal to ID plus IB. So when we first start, so let's say this is your drain current. When we first start, the drain current is actually 0. So what will happen is all the current is going to flow into the gate and charge this capacitor here, right? CGS capacitor. So as the gate source capacitor is getting charged, then your ID is going to slowly increase, and then eventually it will become equal to the reference current. Whereas if you look at the base current, that base current will start with this 80 microamp because it has nowhere to go. So it will start with, so let me put this as green, let's say. So let's say this is your base current. So that base current will start with 80 microamp and will start reducing because these two currents have to be equal to this thing. So that's how, so there is a time transient involved in it, sorry. There's a transient involved in it. So initially when we start, the gate source voltage is 0, but this current source will keep charging it. And at steady state value, the ID has to be equal to that. So if I look at the VGS, again, the VGS is, will follow the same trend. It'll basically follow this trend. So it'll be 0 initially, and it'll start going up till it reaches that value of whatever we calculated before, 0.98 volts. Right? So that's how you'll create that VGS. So now you have the two recipes on how to make a current mirror, right? So for example, so you created this. So basically you take this current and force it into this diode connected transistor. And the reason it's called diode connected transistor is because of BJTs actually, because during the BJTs days, or not, I shouldn't say BJTs, you still do that. You would do the same thing. You would connect it and put the current source here, but this is nothing but a diode, and that's why they're called diode connected transistors, right? And you created the second device over here, and in order to, so let's say this was 80 microamps, and you wanted to generate 80 microamps here, and you said, oh, I want 0.9818 volts here. You said, oh, actually, if you give me a VGS of 0.918 volts, I'll get 80 microamps. And I said, okay, I can generate that by creating the same device. So I created a same device, 100 micron by 1.6. I forced in 80 microamp, and this actually generated that 0.918. And this needs 0.198. So I just basically joined them, right? Because this gate to the ground is 0.918. This gate to ground, I need 0.18. And that's essentially what a current mirror is, right? This is a simple current mirror where you just take the diode connector transistor and connect it. Okay, so the output voltage compliance. So I said, okay, you took um, um, you took a 80 microamp source here, you plugged it in here, you generated that voltage, and you actually generated I out equals to 80 microamps too. So the next question is, what is the region of validity? I call it compliance. What it means is essentially it means if I draw this, and this, let's say this is V out, so this is V out, and this is I out. So for what values of V out is this current mirror valid? And let's say the output impedance is very high, so it'll follow this curve, right? So this looks like a current source, and let's say this is the point where it becomes equal to your input current source 80 microamps, and this usually is the voltage V effective, right? Which is what? VGS minus VT, and we calculated for the previous example, it was 0.118 volts. So in other words, for this to act like a current mirror for the value you are designing, you want to make sure that the voltage across this is greater than V effective, right? So that's when it looks like a current mirror. And that's very important because whenever you design circuits, that will decide, what kind of cascodes and all that you can use. Okay, so the next thing I want to cover is the output impedance, because so far I've been saying that the current we said is constant, but that's obviously not true because it has a so this is, let's say, V out, and this is I out, and it's not constant like as we showed before in the devices, so it's actually has a slope to it, and this slope is the output impedance, RDS, or sometimes we call R out or RO, just simply RO. So if I calculate it, so I'm going to take the same example like before, but instead I'm going to make this 20 microamps now. So let's say I have this 20 microamps. So I'm going to size this to be 25 micrometer by 1.6. It's the same NMOS like the previous one. So if this is also 25 micron by 1.6 micron, then this I out is also going to be 20 microamp nominally. So when we say nominally, that means basically we're ignoring the output impedance, right? Now let's say we want to find out what kind of error we get from the output impedance. So for this, I think we're using a 0.8 micron technology. So this is the NMOS. And if I look at the table, the lambda by L is 0.12. So lambda times L is 0.12 micrometer per volt. And you can, I think you're all familiar with this equation now. So if I just do 1 over lambda ID, and we've already said that typically we assume that this change in current because of the resistor is small. So this ID, we can just take the nominal ID of 20 microamps here. And if you calculate that, I've already done that for you guys. So I think it comes out to be 660. Always verify my calculation. I might have made some mistake. So that's the output impedance, right? So if I want to find out, let's say the voltage is changing, some value, let's say it's changing. So the output voltage is changing by, let's say, amount delta V, which I'll take some example. That's a 0.4 volts. Just an example. And I want to find out for this change, what is this delta I? So that delta I is nothing but this delta V over RDS, which is 0.4 over 666 kilo ohms, which is roughly, I think what's 0.77 microamps, right? So if I look at the error with respect to 20 microamps, so 0.77 over 20, that's roughly 3.8%. So if you vary the voltage, if you have this output impedance and you vary the voltage by 0.4 volts, that's the amount of change in current you'll get, right? So that's just to show one of the non-idealities of the ideal current mirrors we're talking about. Okay. All right. So this is, we're looking at it in a large signal model, but when we do a lot of our small signal analysis, this serves either as an active load or even as a current mirror. When we do small signal analysis, we need to find the small signal equivalent of this, right? So we follow the same. I wouldn't go into the details of it, but I'll just quickly touch on how you find the small signal model. So if you look at the input side, that's your input side, and if you just draw simply the small signal version of this, you draw the gate. So that's your gate, drain, and source, and the gate to drain are connected, right? This gate to drain is connected here, so that's why you have it short. So the way you find out output impedance is you actually apply a small signal voltage, right? You apply some voltage, in this case, for example, Vy, and you find out what's the current being drawn out of this Iy. And whenever you draw this, whenever you do this experiment, make sure all your independent sources are zero. Independent sources. So since this is a small signal model, independent small signal sources, are zero, right? Which is voltage sources are short, current sources are open, you do all that, right? And you end up with this model. So if I do the same experiment here and I find out what Iy is, and Iy is nothing but, if I sum these two current, this is GM1 times VGS, which is nothing but GM times Vy, right? Because the gate to drain are shorted here, over here. So that's GM times Vy plus Vy over the output impedance of that transistor. Now, this is nothing, I can write it in a different way. It's Vy over 1 over Gm plus Vy over 1 over RDS1 or RDS. And this is nothing but two resistors in parallel. One is a resistor of a value 1 over Gm. Another is a resistor of value of RDS1, and that's your output impedance. But typically, um, 1 over Gm is much, much smaller than RDS, in this case, RDS1, right? So then your output impedance, R out, or is just equal to the RDS of that transistor. I'm sorry, 1 over Gm. So this is 1 over Gm. Actually, I'm sorry, I shouldn't say R out. This is R in. Because like as I said, you are trying to create a current source, and this is your ammeter, right? This is measuring the current going in. So this is usually your I reference going in. So typically you want this to be a low impedance node, like ammeter is a low impedance node. Now the 1 over Gm, because usually Gm is large, so that's why R in is also small, and that's what you need, right? And sometimes it's not small enough, but um, we'll talk about that when we get to more specific problems. All right. So that's the input side of the small signal model. Now, if you look at the output side, so you have two sides to the current mirror. This is to ground. That's So we just looked at this here. We called it R in. Now we want to look at this output, and that will be our R out. And you do the same thing again. You take the output transistor and draw the equivalent small signal model, which is this, right? And you do the exact same experiment again, where you put a voltage source here, some voltage source VI, let's say, with respect to ground, and you find out what your IY is. This is VY. And in this case, VY over IY is nothing but just, in this case, we can call this RDS2, because this current is 0, right? Because it's VGS2, and VGS2 is a independent source, because IN is an independent source. So usually I make this equals to 0. So if that's 0, VGS2 is 0, which means this term is 0. So your output impedance R out is simply RDS of that second transistor, right? So your small signal just simply looks like 1 over GM on the source side, source current side, so on the IN. So let's say this is your IN, and on the output side, it's just the output impedance of the transistor. So that's your small signal model of the current mirror, right? Okay, any questions so far? Okay, so any questions?
Hello.
Yeah.
Sir, how is the pristine source different from the normal source?
I'm sorry, repeat that. The pristine source?
Yes, sir. How is the pristine source different from the normal sources we use?
Okay, when you mean by normal source, what do you mean? The normal current sources, you mean?
Yes, sir.
Yeah. So far we've been saying that this is a mirror, right? So it needs a source to mirror it. So for example, if I have a source only, I can mirror it. None of these, the ones I have explained so far, will generate current. They can only mirror the current you give them, right? So that pristine source is a current generator. And that's a little involved. So what you need is what's called a band gap. And we'll actually have a project related to the band gap. When we come to that, we'll realize. So essentially the bottom line of the band gap is we use a BJT, a difference of 2 BJT voltage across a resistor to generate that current. So we'll create a VBB1, VBB2, and apply that voltage across a resistor, and those two voltages are usually pretty constant, and that will actually generate the current. And once we get that current, we can just mirror that, okay? So for now, you just assume that that pristine source is given to you. When I mean by pristine source, it's a pretty non-changing source, okay? So because the mirror, only thing it can do is if you give it a source, it'll mirror it. It cannot create a current source. So in order to create it, we need a different circuit. So don't worry about that right now. Okay. I think there's a little bit of a buzz. Maybe the microphone is on. Can you switch it off? Okay. I think I just wanted to quickly cover the problem. One of the problems I gave, I think the 3.1, 3.33. I think the 3.1, we've probably covered it because I've been slowly developing it. So essentially it was the problem where this current mirror was given, and I think this I in was, this was 80 microamps was given to you. And I think the sizes were given to you. This was 100 micron by 1.6 micron. And this was 25 by 1.6, right? So you can see straight from here, if you assume that there is no output impedances in these two transistors, then this current over here is going to be, because this width is 4 times, because if you look at the equation IDS, that's beta, which is mu times Cox, W over L times VGS minus VT square, right? Let's assume the lambda is not in the picture. So if that's the case, beta is the same, L is the same, this VGS is the same. So if this is 1/4 of this size, that means this current is going to be 1/4 of 80 microamps. So that's going to be 20 microamps here, right? And I think the RDS of this I've already calculated. That was 666 kilo ohms in the previous slide. And the V effective was 0.118 volts. So 0.118 volts. And I think the VGS from that you can calculate it to be 0.917 volts, right? And then I also followed that example where I changed the output voltage and give you the output current change. Now I'll go to the next part of the problem, which I think was given a lot of variations. And this is a very important problem because when we start doing projects, we'll see that there are a lot of variations in VT, mu, and Cox, which are called mismatch of these transistors. And that'll create a mismatch in the current. And that creates a lot of non-idealities when you're designing amplifiers or just simply current mirrors. So I think the first part was if you have a VT change. So let's say we've been assuming that in the current mirror, the threshold voltages for both the transistors are the same, but if they're not same, so let's say we call the first transistor VT as VT1, and if I take the second transistor, let's say it's VT2, then let's say that's 5 millivolt. So I think the question is, what will be the change in the current? Now, if you write the equation for the current again, so ID times beta times W over L, VGS minus VT minus, well, let's say this is plus, so this is, let's say 5 millivolt square, right? So that will be the current flowing into the 20 microamp leg, because I know this VGS minus V effective, which we calculated to be 0.118 volts. We know the W over L, that was 25 micron by 1.6 micron. Beta is from table 1.5, which was 92 microamp over volt square. So if you put all these values and calculate, I've already, I think, done the calculation here. So that turns out to be 21.74 microamps, right? So this is 1.74 microamps larger, which if you do it percentage-wise, is about 8.73% error. So in a typical IC, actually, again, we'll talk about it, more about it when we get to specific problems. The VTs are not the same. They're because of process non-idealities, the VTs of a nearby transistor will actually change. So this is a good sort of example to show that if it changes by 5 millivolt, your current is actually off by almost 10%. So when we do layouts of the transistors, we'll actually try to put them in such layout patterns to minimize this delta VT variation for this region so that we don't get this variation, okay? The second one, I think, it's asking you the same thing again. It's basically asking you the change of the current if the mu and Cox, the beta, is off by, so delta beta, let's call it delta beta, is off by 5%, right? So that's, I think, the problem. So again, if I take this equation over here, so ID, I can write it as, now instead of beta, I'm going to write it as 1.05, right? So let's say it's 5% more times beta, right? So that's your mismatch, W over L times VGS minus VT square. And this is nothing but 1.05 times the current we calculated, which is 20 microamps. And essentially it's a 5% error just because it's linear relationship with mu n. So if you get 5% error in beta, you get a 5% error in your current. So this will be 21 microamps, right? So, and that's again another imperative you get in real ICs. Your nearby transistors don't have exactly the same mu n. They'll vary actually, and if they vary, you get a variation in your current too. Usually they're not this big, but they can be. And the next question is asked if the delta L is off by, I think in the problem it says 0.4 to 0.04, but I think in the previous problem it's 1.6. So I'm just going to say the delta L is the same percentage, which is 0.08 micron, right? Again, this equation, you can write this as ID equals to beta times, sorry, I forgot the equal to sign here, equal to beta times W over L, but I'll write this as L plus delta L times VGS minus VT square. And if you just do a simple, so let's say this, I wrote it as L times 1 plus delta X, and this delta X is your percentage error. So in this case, I think the percentage is about 5%, the 0.08. So because the delta X is small, I can just do a Taylor expansion of this, which is nothing but 1 minus delta X of the ID I calculated before. Let's call this, some ID dash, which was 20 microamps before. So it'll be off by 5%, so it'll be 19 microamps.
Excuse me, sir.
Yes.
So delta L is 0.42.
Yeah, no, I just changed this in the problem because I think it said 0.02 for a 0.4 micron, which is a 5% change in delta L. But actually the problem I think the problem I've been taking so far, the delta L is, the L is actually 1.6 micron. So if you take 5% of this, that's actually 0.08. So I just changed the problem. You can do the same calculation for 0.04. I just wanted to keep the same percentage. So basically what I'm saying is that this 1 plus delta X is 1.05. It's a 5% error in L. And if you have a 5% error in L, you get a 5% error in your current. So this is roughly 5% as well. Okay? That makes sense? You have any questions?
Okay, sir.
All right. Okay, I think that's all I wanted to cover in that. Okay, so the common source amplifier, I think we have been dealing with it so far. So so far we've been drawing the current, kind of connecting dots here, because so far every time we draw the common source amplifier, we draw a current source, some IB here, and then the common source, and then we say, oh, we bias this to some voltage VB, VG, and then give a delta VI, and your output will be some delta V out, and the gain is delta V out over delta VI, right? So now we want to find out the small signal equivalent of this to find the small signal gain. So this current is actually replaced with this current source, right? So this current is replaced with this current source. And like as we said before, the output part of the current source is, if you look at the small signal, is nothing but just a resistor, which is RDS2 in this case. Let's say that's for Q2. And for this, we follow the same small signal principle where we have some VI, maybe some input impedance Rin, and that's your gate voltage with respect to ground. And then from drain to source, you have GMVI in this direction. And then you have the output impedance of this transistor Q1, which I'll call it RDS1. And you also have in parallel, because this node is ground, right? Because once you take small signal, all the DC sources will become ground. So this is ground. So this RDS2 is from V out to ground as well. So that's RDS2, right? RDS2, and this is V out. And if you do the small signal analysis, I won't go to the equation, but it'll be clear to see that V out over VI, that's your small, your small signal gain, let's say call it G. That's nothing but GM times RDS1 parallel with RDS2, okay? I'm not going to go into the problem right now because I think it's just pretty straightforward, but do you have any questions for this problem? So essentially, if you want to get a certain gain, you just follow the method. If you're given a current, you have to find the GM. You can size the W over L, or given voltage, you size the W over L to get the current. It's basically the same process. And if for the given gain, let's say I say, oh, I want a gain of 40, let's say. Obviously, you have two variables here. You can either get high RDS, low GM, or high GM, low RDS. That will depend on the constraints I would have given you. Like, for example, if I tell, oh, your current is, I don't want more than 1 milliwatt of power. So let's say this was 1.8 volts, or let's say I say I don't want more than 1.8 milliwatts of power. Then you're fixed. You can't be more than 1 milliamp of current here, and you kind of go from there, right? So again, once we start doing specific problems, maybe we can discuss the details, but there's nothing really much. And yes, I've ignored the GS term over here because again, I'm assuming that the bulk is actually connected to the source here. So I think the second part of I think the last part of the problem was source follower. Again, I think it's kind of almost out of time right now. But the source follower, what I'll do is I'll explain it to you in large signal model part, and we'll give you the solution, and you can look through the solution to, it's again a straightforward process of, replacing this with RDS 2, and then replacing with a small signal, and then finding out V out over V in. Now, show you the concept of this. So usually we'll be using a source follower a lot, and it's usually for impedance matching. Okay, what do I mean by impedance matching? So this voltage V in, let's say this source has a really high output impedance. In other words, this source over here, let's say that's some small signal source here. It could be like your microphone, for example. So let's say you have this source and this output impedance is very large. So this, I'll just call it RS. So let's say some VS RS, and this VS, let's say it's large. Then whatever I'm driving it to, this impedance should look very low. Otherwise, this will load it. For example, let's say this is, I'm just going to put 100 kilo ohm, let's say, and let's say this load is 1 kilo ohm, right? Then you've lost the gain. So this V out is, 1K over 500. I mean, sorry, 1K over almost 1K over 100, 101, which is almost 0.001, right? So it's a gain killer. I can't do that. So that's when I use this stage. So basically, I'll take this, put it at the input. Now the input looks really high input impedance because it's a cap, right? And then this drives a load. So now I can put a load here for 1 kilo ohm, and that'll be able to drive it. Now it's called a source follower because this source actually just follows the input ideally. Now what I mean by ideally is if I write this equation again, so let's say this current is some IREF, right? And if I write this current for ID1, so let's call this ID1. Again, it's beta times, I'm assuming it's always inactive. So it's beta times W over L VGS minus VT square, right? Or V effective square. So VGS is what? This is beta times W over L. VGS is V in minus V out, right? VT square. Now, if this current is not changing, let's say this is 100 microamps, right? So let's say this is 100 amps. This current is not changing. This is fixed. This is fixed. This is fixed, which means that V in over V in minus V out should be fixed also, which is, let's say, that DC bias VGS 0. In other words, V out is nothing but V in minus VGS 0. So this is fixed. So that means if I have some delta V in, that will be exactly equal to delta V out. That's what it means that it follows, is a source follower. So usually it's a gain of 1, but in reality you have some output impedance here, some output impedance here. If I put the load, the gain won't be 1. So I think in your problem it says that the gain is 0.8. But that's really what a source follower means. So source follower is the matching impedance. So I take a voltage source like a microphone, or maybe your MP3 player or something like that, which has a high output impedance, and I want to drive your speaker, for example, which is 8 ohm, right? Let's say you have a large speaker. Then I need a buffer like this. It's usually called a source follower, or usually called a buffer, because you want to buffer your load impedance from your source. Otherwise, it'll just kill the gain. And we'll use this in a lot of the amplifier stages. We'll look at it in more detail when we go into it. Again, I'm not going to do the small signal. I'm run out of time right now. But you can look at the problem. It's pretty straightforward. And if you have any questions related to it, you can always ask me. Maybe in the next lecture, if you have any questions related to it, I can answer that. Okay. So I'm going to just stop the recording now, and then maybe we can take questions.